All righty.
Confused about that. I don't really know that anymore.
So, let's finish up our notes from yesterday. Okay. And then we'll get into the partial fractions. That's the homework from yesterday, or from last night, if you wanted to check it. All right. So, solve the differential equation for y equal to f of x given dy dx equals y ln x and f of 1 equals 1. So, right, if you remember yesterday, we learned integration by parts, right? And now we're going to finish up with a problem here. Well, two problems, I guess. One being Mr. Goff's favorite, bless you, and the other one being this one right here. Okay, because I would like to finish it up, even though I kind of, gave you a good shove to kind of get it done, on your own if you wanted to. But anywho, we're here, so let's do it. So we're, again, solving a differential equation, right? Separated our variables. We had 1 over y dy then equals natural log of x dx. We integrate 1 over y, no problem. It's natural log of the absolute value of y plus c. Integrating the natural log of x, though, we don't know that, right? We don't have a rule for it, okay? But we can do it now using integration by parts, all right? Using our hierarchy, I latte, okay, right? We don't have any inverse trig, but we do have natural log. So we're going to let u, in this case, be the natural log. Okay? Be careful, right? That mnemonic device, I latte or I late or however you want to remember it, right? That is for choosing our u. Don't get that confused with choosing dv, because you have to choose two things here, really. Okay? But we choose u using that I-L-A-T-E kind of hierarchy. All right? So be careful with that. Anyway. We've got the u equal ln x there. Dv was equal to dx then, from what's left over. So then du would be 1 over x dx, and v is x. So we'll go ahead and just do our uv, which will be x ln x, minus the integral of v, which is x, and then du, which is 1 over x dx. Okay. So x times the 1 over x, that simplifies to just what? 1, right? And we're going to integrate 1, and so that's just going to be x, okay? And so we end up with the natural log of the absolute value of y plus c equals x, natural log x, minus x. And then I guess I don't have to put a plus c over there because we already have 1, so never mind. Okay, so minus x like that. All right. Now, we're not done yet, right? We're supposed to solve the differential equation for y equal to f of x. In other words, we need to have y by itself equal to stuck with x on the other side, right? And we also need to figure out what c is as well. We have a particular, solution there. So again, your choice. You can choose to solve for y first, then plug in your 0.11 to solve for c, or you can, plug in 1 first, then solve for c, and so on and so forth, right? So plug in 1 first. All right, that's what I heard. We'll maybe do both here just to see if we have time. I'm going to first of all move the c over and just put the plus c over there. Okay, Mr. Witt, it's algebra. Shouldn't you subtract c from both sides? Yeah, I could subtract c from both sides, but also because, again, it's the constant, the sign will just adjust there. And so you can just make it plus c over there. It doesn't really matter. Okay, but yeah, at this point, I'll go ahead and just plug in the 1, 1. Okay, so it'll be natural log of the absolute value of 1 equals 1 times natural log of 1 minus 1 plus c. Okay, natural log of 1 we know is 0. And then 1 times another 0 is 0, minus 1 plus c. Okay, so c is 1. Okay, and so we get natural log of the absolute value of y equals x natural log x minus x plus 1. Okay. But of course, to finish solving for y, right, to get y by itself here, what do we need to do to both sides? E, okay, we're going to do, e to the left-hand side, e to the right-hand side. I'm running out of space, so I'll just kind of arrow over here. And so we end up then with y, excuse me, equals e to the x natural log x minus x plus 1. Okay. And again, in this situation, right, I kind of like dropped my absolute value, right? I had natural log of the absolute value of y, but I know it's going to be the positive version, right? I know I need to be a positive e here because of this initial condition, right? My x value is going to be 1, and my y value needs to be positive. Well, the only way I can guarantee my y value is positive is a positive e here, not negative e. Okay? Or for that to work out there. So there's my y equals there. All right, and I'll just quickly, in case for those of you that like to solve for y first. So if I solve for y first here, we would do the e to both sides there, and we get y equals e to the x ln x minus x plus c. Remember, when you have that plus c there up in the exponent, you can bring that c out front and make the constant be y equals c e to the x natural log x minus x like that. Okay. And now you can plug in the 1, 1. 1 equals c e to the 1 natural log of 1 minus 1. Natural log of 1 is 0, times 1 is still 0, minus 1, so it's c e to the negative 1. Okay. Which is really, you know, c over e. So we'll multiply both sides by e, and we get that c equals e, the number e, right? Okay, and so then our equation there would be y equals e times e to the x ln x minus x, like that. Okay, if you chose to do it that way. Okay. Take a 30 seconds here to convince ourselves that these two things are the exact same, right? This e is e to what power? E to the first. When you multiply two things that have the same base, right, they're both base e, what do you do with your exponents? Add. So it's going to be 1 added to this. Well, there it is. Now, x natural log x minus x plus 1. And then plus 1 go at the end or in the front or wherever you want it. Okay? So they are, in fact, the same thing. And that's a good thing. All right. Questions on example 4 there? Okay, yes, Sean.
What if you got your c to be negative 1 by keeping the c on the side of the L and y earlier? Is that okay?
Yeah, that's fine because understand, right, we're still going to have to end up solving for y. That c is going to move over, become a plus 1, and then voila, same deal. All right, now on to Mr. Goff's favorite problem in all of calculus.
I already hate it.
You already hate it. Oh, yeah, it's a good one. You realize what it is now? Okay, well. So, let's take a look here. We're going to evaluate the integral of e to the x sine of x dx. Now, granted, this is not like, I think Mr. Goff likes this problem because of the strategy that we have to use, not so much that it's just this problem, right? This kind of strategy can show up in other ways, okay? So it's not like this specific like formulation, okay? It's just this formulation leads to the strategy that I think Mr. Goff really likes, okay? So you might see this again, right? Kind of thing. Anyway, all right, let's do our integration by parts here. So we'll let u, okay, be, and then what should we choose our u to be in this case? Sine of x, right? Okay, so yeah, trig is right above in the hierarchy. It's right above exponential. So we're going to choose the sine of x first, and hopefully that will lead us rightly. Okay, pointy dv there, and so that means dv has to be e to the x dx. Okay, so we integrate both sides there. So that means v then is just e to the x. Well, that's easy enough to integrate. Makes it easy for us. And then the derivative of sine is cosine dx. Okay, so easy enough here. uv, so e to the x sine x, minus the integral of v e to the x cosine x dx, v du. Okay, now what do we get to do? Another integration by parts. Woohoo! So I'm going to put ones here. Again, I don't know if this is necessary, but I'm going to do it, just because. I'm going to say let u, so 1 equal that. Okay, and so we'll have to do another integration by parts. So we'll say let u2 equal, and so what's our u going to be in this case? Okay, yeah, cosine of x now. Okay, and then dv will be then e to the x dx again. Okay, again, dv sub 2 there, I guess I'll say. Okay, so du sub 2. Derivative of cosine, negative sine. Okay, and then the integral of e to the x, ec e to the x.
Just going to keep going.
Just going to keep going forever and ever. That's true. That's a good point. All right, so let's see what the next one is, but I think Mike's onto something there. Okay, this is why it's Mr. Goff's favorite problem, is because it never ends, and he doesn't want calculus to ever end, I think. Okay, so well, I mean, this is like a limit almost, as the problem approaches infinitely long. All right, so e to the x sine x minus, and then quantity uv, e to the x cosine x, minus the integral of v, e to the x du negative sine of x. Okay, now let me simplify this just a little bit, and I'm running out of space, so I'm going to take this, I'm going to move it down to here, okay, and rewrite it here. So what we've got right now is we're trying to evaluate the integral of e to the x sine of x dx, right? That's what we're trying to find. That's the original, integral we're trying to find. And I'm going to skip over this step we just did and say, okay, we know this integral of e to the x sine of x dx, it's going to equal this thing right here, which is e to the x sine of x minus e to the x cosine x. And then the minus and the minus become plus, but then there's the minus from the sign there, okay? So it's plus, but it's another minus. So it's going to be minus the integral of e to the x sine of x dx. Okay, again, the minus in front of the parentheses would distribute to this minus and make it plus, but then because the sign is negative, overall, it's going to be minus e to the x integral e to the x sine x dx. Okay, so there is what we started with and where we are right now. Okay, and Mike correctly identified that we're going to have to do another integration by parts here. But what do you notice about this integral? It's the exact same as this one. So we can use algebra here, right? And we're going to add integral e to the x sine x dx to both sides to cancel out this integral over here. All right, I'm going to do this like old school style where I actually write it underneath, Back when we first learned how to do solving equations and stuff, maybe you did this. Okay. If I have a minus integral e to the x sine x dx and I add integral e to the x sine of x dx, what happens over here? They cancel. Okay. If I add these two together, what are we going to get? 2 integral e to the x sine of x dx, and that's equal to e to the x sine x minus e to the x cosine x. And then how can I finish solving here? Divide both sides by 2, or multiply by 1/2. I'll put a plus c there at the end now. Okay, and there it is. That's our answer. Okay. So this kind of strategy is employed when we have this kind of cyclical nature, like Mike correctly identified it here. When you kind of see you can just keep going forever and ever and ever, right? Because you're gonna keep doing the same thing, and it's just gonna repeat itself, right? Well, eventually, because of the cyclical nature, you're gonna get back to what you started with, and so you can take that final integral, add it back over, and then solve that way, okay, using this strategy. Okay, so this really is only going to occur with things whose integrals and derivatives again occur in cycles, right? E to the x sine of x, both of those kind of cycle as you take their integrals or take the derivatives. They cycle around back to each other, right? Whereas that's not the case with the natural log, right? So you won't be really, I wouldn't expect you to employ this strategy when you're using natural log and stuff like that, because the derivative of natural log leads you down one path, the integral of natural log leads you down a different path kind of thing, and never the two shall meet, right? Whereas here, integrating or differentiating sine of x, you're going to eventually kind of repeat yourself. Same thing with e to the x as well. Okay, so this kind of strategy, you're going to notice more when you're doing those cyclical kind of problems, okay, that don't really end otherwise. Okay. Anywho, so there's our final answer. I'll circle that. All right. Questions on any of that before we move on to technique numero dos? Okay. Well, then let's turn the page here. All right. So, next strategy we're going to learn, all right, is something called partial fractions. All right, so this section takes a look at a technique in which a rational function, rational, right, like a fraction, right, rational numbers or things can be written as fractions, right, so a rational function, functions are going to be written as fractions. We're going to decompose it into simpler rational functions, simpler rational functions to ease our integration process, okay? Before we're going to incorporate the integration, the calculus part, let's just kind of see what it looks like to decompose two rational functions, okay? So before we even do that though, so I'm going to do one other little problem here and just kind of show you what I'm talking about. So if you remember from maybe pre-calculus or something like that, or maybe algebra 2, okay? If we wanted to do a problem like this, 2 over x minus 2 minus 4 over x plus 3, if we wanted to put those things together, okay, well, they're fractions, and what do you need in order to combine two fractions together? Common denominator, right? And so you look here, aha, so this denominator has an x minus 2, this denominator has x plus 3. So if I go back to my first denominator there, okay, x minus 2, what is x minus 2 missing? What's our denominator over here missing that this one has? An x plus 3. So we would multiply this one, right, times x plus 3 over x plus 3, multiplying by 1, so we're not changing the value of this, but that then gives us 2x plus 6 over x plus 3 times x minus 2. Right? Here, I'll zoom in some more on that. Okay? Over here, right, to get a common denominator, well, we have an x plus 3 already, but we still need a what in the denominator here? We need an x minus 2, right? And so we'll multiply this one by x minus 2 over x minus 2, so we get a common denominator with the denominator over here, right? This one gave us an x plus 3 over x minus 2 in our denominator, not over, but x plus 3 times x minus 2, so we're going to get the same thing here. We'll have minus then 4x minus 8 over x plus 3 times x minus 2, like so. Okay? Right, so far so good. That's what we did. And then we could subtract these things, all right? And so it's going to be 2x, so it'll be negative 2x, and then plus 14. Okay, 2x, or negative 2x plus 14 there, okay? Remember that minus sign in front of the fraction, it distributes both to the 4x and the minus 8. If you want to make it easier for yourself, you can do a plus, add the opposites there to make it more obvious, Okay, it's really a negative 4x there, and then an 8 and 6 add up together. And so then we can leave the denominator x plus 3 over x minus 2 like that. Okay, and so adding these two things together, right, results in this right here. Or if we multiplied it out, I guess I can do one more step further here. Negative 2x plus 14 over x squared, let's see, be plus 3x, but minus 2x, so plus x, and then minus 6. Okay, so this became this. All right, that became that. All right. What we're going to do today is take this, right, and make this right here. Okay? Partial fraction decomposition. We're going to take a single rational function, decompose it into a sum or difference of two or more, okay, rational functions. Why? Well, because to integrate this, right, imagine trying to integrate this, right? You might say, oh, well, let's just let our u be the denominator, right? Let u be x squared plus x minus 6, but then our du would not quite match up to our numerator there, and so you'd be kind of stuck. And then you might be like, well, Mr. Wood, maybe we broke up the numerator. Again, you still kind of might be stuck there with breaking up the numerator. It wouldn't quite work out that way either. But with this, we can integrate these no problem, right? This is going to be a natural log. It'll be like 2 natural log of the absolute value of x minus 2. And this will also be a natural log, right? 4 natural log of absolute value of x plus 3, right? So this is much more easy to integrate than this is. And that's why we do partial fraction decomposition. Okay? So let's see it in action here. Okay? Again, we're not going to be worrying about the calculus right now. We're just going to take this single fraction and decompose it into 2 or more fractions there. All right. The first thing we got to do is figure out, okay, how many fractions we're going to decompose it into, right? And so if we look at our fraction right here, we can rewrite our denominator, right? There it is, x squared plus x minus 6, okay? So we're going to have the same denominator as we kind of did over here. That factors to be x plus 3 and x minus 2. So 4x plus 7 over x plus 3 times x minus 2, right? That's equivalent. No mathemagic there. We're just kind of, factoring. Which means then we ought to be able to break down, we ought to be able to decompose this single fraction into two fractions, one that has a denominator of x plus 3, one that has a denominator of x minus 2. The question is, right, how do we solve an equation here with, well, really 3 variables, right? But we're really interested in finding a and b, right? How are we going to solve this? Well, let me show you here. So let's start by rewriting this kind of problem that we've created for ourselves, or that I've created for you. You're welcome. Oops, sorry, I'm off the screen now. Let me zoom out some. There we go. Okay. Now, what we're going to do here is kind of like, I guess you can say we're going to kind of like clear the denominator, so to speak. Okay, so we're going to take this side, and we're going to multiply by x plus 3, x minus 2. I'm off the screen again. Let me just zoom in over here, because I don't need to have that other stuff anymore, I don't think. Okay. So we're going to multiply the left-hand side by the quantity x plus 3 times x minus 2. So those will cancel, and our left-hand side will be 4x plus 7. Okay. Then over here, if I do the same thing on this side, multiply by the quantity x plus 3 times x minus 2. Well, so now we have some addition in here, so this quantity is going to distribute, right? And so really, it's the b that gets multiplied by the x plus 3 times x minus 2, but also the a is going to get multiplied by the x plus 3 times x minus 2, right? Those both, it distributes that product, right? Here, this is just one thing, and so we get quickly, kind of cancel out, but this distributes both to the a fraction and the b fraction there, okay? When we distribute the x plus 3 times x minus 2 to the a fraction, what will cancel? The x plus 3's will cancel, so we'll have a times x minus 2. Okay? When we distribute x plus 3 times x minus 2 to the b fraction here, what's going to cancel there? X minus 2, so we're going to have b times x plus 3. Okay? So now we have this relationship. All right? Now we have this relationship. So, with this equation, all right, we can kind of make some choices about what we want to let x be, right? So for example here, what might be a good choice for x if I wanted to try and solve for, let's say, letter A? What might be a good choice to pick for x if I wanted to solve for letter A here? -3. Why, Sarah? If I pick x to be -3 here, I can plug a -3 in here, -3 in here, -3 in here. But -3 plus 3 is going to be 0. The b will cancel then. The b will disappear. And we'll be able to then solve an equation that has only a in it, right? And so that's exactly what we're going to do. So let's say x equals -3. Then we're going to have, let's see here, -12 plus 7, so -5 equals. And then -3 minus 2 is -5, -5a. Plus, and then it'll be, yeah, b times 0. Okay, so that's just going to go away. And so then a is going to be just 1. Oops, I'm off the screen. There we go. Okay. What's going to be a good choice to help us solve? What's a good choice for x to help us solve for b? 2, right? Same principle. We want to get rid of that. We want to get rid of the a term there, so we'll just use 2. So we'll have then, let's see, so x equals 2. We'll have 8 plus 7, so 15. Okay, equals, and then it's going to be 0 times a. Plus, and then 2 plus 3 is 5, so 5b. And so then b is 3. Excuse me. All right. And so then our decomposition here, 4x plus 7 over x squared plus x minus 6 must equal, excuse me, must equal 1 over x plus 3 plus b over x minus 2. Okay, why b? 3 over x minus 2. Okay, like that. Much easier to integrate, right, than this would be. Much easier. And that's why we do it. Okay, and again, that's our decomposition. That's our decomposition. Okay. Let me show you one alternate way to think about this, all right, before we move on to the next one here. Let me show you another alternate way to think about this. Another way to think about it is to go back to this kind of like initial kind of equation we started with right here. So let me show you an alternative here. And let's say we instead continued from here and just said, all right, let's let 4x plus 7 equal ax minus 2a, and we'll distribute the b here, plus bx plus 3b. Okay. Off screen, thank you, sorry. There we go. Okay. So again, all I did was just take the a, distribute it to the x in the minus 2, took the b, distributed it to x in the plus 3, still have the 4x plus 7, that it was equal to over there. Okay, this is an alternate way to think about it. To do what we just did, an alternate way to do it. Okay, in this case, right, the different kind of strategy we're going to use here is, well, we have two x terms, ax and a plus bx. Okay, and ax and bx together have to combine to make what? Ax and the bx, right, they have to combine together to make 4x. So in other words, a plus b has to be 4, right? This minus 2a, this plus 3b, they have no bearing on the x term because they don't have an x with them, right? These don't have x's, but these do. So really you can just say, aha, a plus b has to equal 4. Right? Because those are x terms. So I can just drop the x's. The a plus the b has to equal 4, right? Likewise, the minus 2a and the plus 3b, they have to add together to make what? 7. All right? They have to add together to make 7. So we can then say, aha, so then minus 2a plus 3b equals 7. And so we have these two equations, and we have two equations and two unknowns. You can solve that using systems of equations, right? So you can use elimination, you can use substitution, you can use, well, graphing, I guess, but, So let me just show you that here real quick. Let's use elimination because it's already kind of nicely set up for elimination. All right, I'll just well, let me do it this way. I'll put the a plus b underneath like that. All right, and so if you guys remember elimination, right, we want to get one of our coefficients to be opposites of one another here. Oops, I'm off the screen. There we go with that. So let's see here. I'll multiply both sides by 2. Multiply this bottom equation by 2. So we end up with negative 2a plus 3b equals 7. And so we then end up here with 2a plus 2b equals 8. And then add those two equations together. The 2a's cancel. 5b equals 15. b is 3. And then once you know that b is 3, you can plug that back into like our original equation here. A plus 3 then equals 4, so a equals 1. And so there's the 3 and the 1 in a different kind of way there. Okay? Using a system of equations instead. Your choice, what you want to do there, okay? Maybe I just made it worse because I've shown you two methods now, and when I give people choice, they're like, no, just show me one way, but there it is, all right? You still get the a as 1, you still get the b as 3, and so you still get your partial fraction decomposition. Okay? Questions on any of that? All right. So, let's try another one here. So write the partial fraction decomposition for 5x squared plus 20x plus 6 over x cubed plus 3x squared plus 2x. So let's factor this thing here. Okay? So, let's see. Looking at the denominator, right, immediately I see there's an x in each of those terms. So we'll factor an x out, leaving behind x squared plus 3x plus 2. Okay? And then can we factor that quadratic further? Yes, x plus 2, x plus 1. So 3 factors in our denominators means we can, and 3 factors in our denominator means we can decompose this into how many fractions? 3 of them. Yeah, exactly right. So we're going to have a over x plus b over x plus 2 plus c over x plus 1. Okay. I'm going to use the first strategy that we use, okay, the first one here, if that's all right with y'all. Okay, so that means we're going to, again, kind of like clear out our denominator. So we're going to multiply both sides. We're going to multiply both sides by x times x plus 2 times x plus 1. Okay, so that means the left-hand side is just going to end up being 5x squared plus 20x plus 6, right? We're going to cancel out that denominator there. And that's going to equal, now when I multiply x times x plus 2 times x plus 1 with the a, the x's will cancel, and I'll have the x plus 2 times x plus 1 left over. Okay, like that. So it's going to be a times quantity x plus 2 times x plus 1 plus b, and then b has an x plus 2, so the x plus 2's will cancel. It'll have an x and an x plus 1 left over. And then c has x plus 1, so that'll cancel, and we'll have the x and the x plus 2. Okay. So questions up to that point. Are we all okay with what I just did right there? All right. Are we all okay with what just happened there? Any questions? Because I don't want to lose anybody here, right? This is like some pretty intense algebra. Yes, Sarah.
Why do you multiply all of them by the denominator again?
So just to kind of help us with simplification's sake, I'd say, because it gets rid of the denominators here and just allows us to then just focus on, simplifying with quadratics and stuff like that. So that's all. It just makes it a little bit easier. Okay? Any other questions on that? Okay. So again, I'm going to continue down that other path here that we chose where we kind of like selected, we were strategic about what x values we chose here. So in this scenario, okay, what might be a good strategic x value to select to solve for one of our variables? So Robert? 0. Yeah, very good. If you look here, right, both b has a factor of x and the c has a factor of x there. So if I put 0 in both of those, they'll cancel. So let's make x be 0. So then we'll have 6 equals, and then, let's see, 0 plus 2 is 2, 0 plus 1 is 1, so 2 times 1, so it's going to be 6 equals 2a plus 0b plus 0c. And so then a is just going to be 3. Okay. Once you've established that a is 3, you can now put 3 in for a and all the other work that you do if you want. You can put 3 in for a and all the other work that you do if you want. But it's not going to be necessary in this case. We'll be able to do this without that. Okay. What's another good strategic x value to use here? -2 would be a good one. Okay. So x equals -2. If x is -2, then the a value is going to eliminate because it'll be just 0. Okay. Let me go ahead and plug it into the left-hand side first here. So -2 squared is 4 times 5 is 20, but minus 40, so -20 plus 6 is -14. Okay. And that's going to be then a 0a, 0b, no, not 0b. B is what we're solving for there. So it'll be -2, -2 plus 1 is -1, so positive 2b. And then it'll be 0c. Okay. And so they end up with b is -7. Okay. And then what's our final strategic x value we want to pick here? Yeah, -1. So let's make x be -1. And so let's see here. We'll have 5 minus 20, so -15 plus 6 is -9. And then we'll have 0a, 0b. And again, you don't have to put the 0a, 0b there if you don't want. You can just, you can just see, oh, it's going to be 0, it's going to be gone. You don't have to put that part. But I'm just doing it now for the notes and stuff. And then let's see, -1 plus 2 is 1 times so plus minus c, so then c is 9. Okay. Whew. And so then all that, we can now say 5x squared plus 20x plus 6 over x to the third plus 3x squared plus 2x is equal to 3 over x plus negative 7 over x plus 2 plus 9 over x plus 1. Okay, no calculus there, right? This is all Algebra 2. Okay, back when I was in high school, we learned this in Algebra 2, actually. I don't know if they still teach that in Algebra 2 now, but this is something I remember doing in Algebra 2. Maybe even pre-cal. I forget now. But anyway, there it is. Okay? So, questions on any of that? The other method with the systems would work here. The catch is that now you're going to have essentially 3 systems that you're going to write. You're going to have, ax squared plus bx squared plus cx squared equals 5. So a plus b plus c will equal 5. Then you'll have your x terms, and they'll all add to make 20. And then you'll have your number terms, and they'll all add up to make 6. So you're going to have 3 equations with 3 unknowns. Ugh, that's not a fun system to solve. So this might be a better way to go, right? All right, moving on. So now number 3. Now we're going to add some calculus in, right? Because why not? It's been too long since we've done it, all right? Yes, this is 2 problems, no big deal. All right, but now this is easy. This is going to be so easy. So, again, let's see here, all right? We have x squared minus x minus 6, which factors to be x minus 3, x plus 2. Okay, and so we're going to equal then a over x minus 3 plus b over x plus 2, right? We want to decompose it into that. All right. Oh, question, Kara.
Okay, so how do you know that we're going to split up the variables in your math? Like, is it just whenever you see a fraction with 3 plus terms in the bottom?
Good question, good question. Okay, so like how do we know, because it doesn't say in the directions here, use partial fractions and stuff like that, right? Like the idea is like strategically, what should I be looking for, those kind of things. So I mean, again, what you do want to look for, right, first thing is just to kind of see, you can I mean, again, on your own in the wild, you can, if you want to, think, okay, well maybe I could split this up as 3x over x squared minus x minus 6 plus negative 1 over x squared minus x minus 6, okay? This, we'll be able to actually integrate this by completing the square here and using like arctangent. Yeah, that one would actually integrate by completing the square and using arctangent there. Potentially, as long as you ended up with a plus instead of a minus. So I have to actually see if that completes the square, if that would work with completing the square. So you might be able to complete the square here and use arctangent. I'll say that. You might be able to do that here. But then here, this is where we're going to run into the issue, right? If you look, you like a u substitution, you might be like, oh, maybe I can make it x squared plus or minus x minus 6. But then your du would be 2x minus 1. We have a 3x, but no minus, kind of stuff there. And so that's where so I'm again just trying to kind of imitate what you're probably going to run through here. Okay, now obviously today, for the homework and stuff like that, you're going to assume most of these are going to be partial fractions, right? But again, on your own in the wild, that's what I foresee you doing. You would try to split it up like this. You'd see, if I let this be u, that's not going to match up. If I let this be u, this won't match up still, kind of thing, right? And so it's like, okay, I can't use a u substitution. If I break it up, like you said, it doesn't work. And so let's try partial fraction decomposition. That's
Everything we're learning is last resort.
I would say, I mean, again, yeah. You want to start with the stuff you're more familiar with, right? Because they're easier, right? And we learn these more advanced techniques because they're more advanced because they take more work, right? And so it's helpful to be familiar with the earlier stuff to know this stuff. So yes, that's what I would say. That's what I would say, yeah. Okay, so moving on here, right? We're going to go ahead and get to what we were doing. So we're going to multiply, again, these 2 fractions. We're going to multiply both sides by the x minus 3 times x plus 2, leaving 3x minus 1 here, and leaving a times the quantity x plus 2 plus b times the quantity x minus 3. Okay? Are we all okay with that jump that I did right there with the algebra? Yes? Okay. Again, I multiplied this whole side by that x minus 3 times x plus 2. And so the x minus 3's will cancel, so that's why you have the a x plus 2. And the x plus 2's will cancel, that's why you have the b times x minus 3. All right. And so what's a good strategic choice for x here? -2. Sounds good to me. Okay, and so we get -6, we get -7 equals -5b. And so b is 7/5. Fractions, ugh, but that's okay. And then what's another good strategic choice for x? 3. And so we'll get 8 equals 5a, so a is 8/5. And so the integral of 3x minus 1 over x squared minus x minus 6 dx equals 8/5 over x minus 3 dx plus the integral of 7/5 over x plus 2 dx. That 8/5 and that 7/5, what can we do with those? Bring them out front, right? They're just coefficients. And so we can make that 8/5 integral 1 over x minus 3 plus 7/5 integral 1 over x plus 2. Okay? Technically here, to integrate now, what strategy do we need to use? A u sub. But it's a very basic u sub. I'm just going to show you for this one, and then you'll get the idea, hopefully, right? So let u equal x minus 3. Du will just be dx. Okay? And so there's not really, like, this is essentially integrating 1 over u. And this also will end up essentially be just 1 over u that we're integrating. And so we can kind of skip that stuff and go right to here. And there it is. Okay. Okay. Questions on any of that? Now, since our solutions involve natural logs, what further steps could we do here to quote-unquote simplify our solution? The 8/5 and the 7/5 can become what? Exponents, powers. And so we could, yeah, I know, right? This just gets better all the time getting better. So we can say x minus 3 to the 8/5 plus. So I can drop the absolute value for. I can drop the absolute value for this one because it's an 8 as our exponent. So that's going to make a positive. Yes, thank you. We have to do this. Yeah. But if it's multiple choice, right, you'll need to be able to match your answer. That's why I'm showing you this here. Yeah, absolutely no. If this is free response, you're done here. Don't keep going, right? But multiple choice, right? Or if you're trying to match your answer in the back of the book or something like that, the book likes to simplify things extremely. And so we can do this. And then there's one more thing we can do. What else? Mike?
When you add exponent or natural logs, don't you multiply them?
Multiply what is inside. And so then it's going to be natural log of the quantity x minus 3 to the 8/5 times x plus 2 to the 7/5. I think I should put absolute values around that one. Okay, and so that's as far as we can simplify. All right, again, I'm not showing that to torture you. I'm showing that because this could be a multiple choice answer that you need to be able to like match it to. Okay, so yeah, Kara, sorry, I think you.
Does the exponent go inside of the absolute value brackets?
I believe it should. That's a good question. Let me think. Yes, I think it should. I think it should. Yes, I think it should. Yes. Gabe.
On these two problems, do we still need the plus C?
Oh my gosh, thank you.
Look at Dave.
Yes. Absolutely. Absolutely. Okay.
What a dog.
Questions on any of that then? Thank you for pointing that out. Yes. All right, moving on. Why don't you guys give this one a try? I think, I've beat this enough into you now, right? No, I haven't? Yeah,
I got it.
give it a try. Give it a try. It does factor. I'll get you that started, right? So it factors to 2x minus 3, x plus 2. All right, so give it a try there. Give it a try there. Okay, so I'll give you that much, and then we'll. the one to try, I'm also going to combine it together as a single logarithm too. Okay, I'm also going to combine my answer together as a single logarithm. This one's not that bad. Not as bad as the last one.
Not that bad.
I guess it's all a matter of opinion, no matter perspective. When you use x equals, so you're using x equals, okay, 3 halves is right, okay, and so then 3 halves plus 2 is 4 halves. You need 3 halves and just add a 2 to the numerator in there, but it's 3 halves plus 4.
I wrote x equals 6 instead of x equals 2.
Don't forget,
I just
what
wrote
you did,
x equals 6.
you did too.
Yeah, you're right.
So close to these values. B is -3 and then A necessity for 6. Yeah. So here it should be that's a 2 x minus 3 there. This when you do want to use it, x minus 7. 1/2 right, so it's going to become. See what I'm saying?
I was gonna show it short.
Same idea. When you use a use substitute, you're going to give 2x minus 3. So your d is going to be 2 dx. So you get the 1 half over 1/2.
So,
Okay. Should be a 3. Yep, okay, they're both different.
wish I had
What?
I have pretty colored pencils.
Alright, we'll move on here.
I'm in 95 and 20. That's fine. I'm pretty bad. I don't know. I need 5 out of 100 on stretch. Okay. 21.
He's gonna give you
Dude, if he gives me a B, I may just off myself. I don't understand how you can do that. Like, I'll commit suicide by it.
I'd say, well, actually, no, this should still work. If you then just do the 21, it should still work. And then yeah, 21 divided by 7 would be 6, and then 21 divided by 7 is 3. Yeah, that would still work then, yes. I'm sorry, yes. My apologies.
What's the larger one?
Large one, something like that, yes. Oh, Ariana, be right there. Okay, there's the solution. You want to take a look? Check the work.
Got it
Yes,
so well.
exactly right.
So well done.
All right, questions there. Questions. And again, you don't have to get it down to there, but you should be able to if you're trying to match some multiple choice, right? We can't drop those absolute values because cubing something doesn't guarantee it's positive. All right, let's press onward and upward here. Onward and upward. All right. So, number 5, the population of Haverford. And when I read this question, I think to myself, was Mr. Goff watching Parks and Recreation when he wrote this question? But maybe not. Maybe Haverford is an actual place. I don't know. Tom Haverford. Anyway,
Go to
Yep.
the last page.
Sorry.
2 seconds.
absolutely, yep. Not a problem.
Thank you.
Okay.
Well, this class is taking forever.
I know. It's hard to go from 60-minute classes to 8-minute classes. But we're almost there. All right. This is these are the last 2 problems.
40 minutes makes it worse.
Okay.
Doesn't it feel like
I swear yesterday was a pretty long day though. Like it felt like, all day.
Yeah. Maybe they'll start, employing me later on when people are.
It's a home day.
we have off Thursday too?
We have off on Thursday? It's just so much snow. I don't know we just have so much snow.
I want a blizzard.
Well, but ice can be worse than snow. So
This is the snow and then freeze rain.
yeah, that's gonna be fun.
I'm okay with it.
We there was in 1994 or 1996, which I know is before you guys were born. We had like really bad snows, and then they would really bad ices on top of that snow, and so you could like sled on top of the snow because it was so glazed with ice.
Really?
Yeah. But then sometimes you'd break through the snow and like cut yourself because you like break through the ice and like slice on the ice and stuff like that. So yeah. It was interesting. It was interesting. Interesting time to be.
I bet you the snowball's pretty nice though.
Yeah, you could hurt some people. Anywho, all right. Population of Haverford is growing at a rate modeled by that, where G of T is millions of people per year, and T is years since 2010. T equals 0 there. Okay. If there are 123 million people in the year 2011, what will the population be in 2014? Okay, so we have like some new stuff going on, but also some old stuff going on here too, right? We have an initial population, well, not initial population. We have a population in 2011, which is 123 million people. Okay, and we have a rate of change of the population in millions of people per year. All right. So, we're going to start with that initial not initial, I keep saying initial. This is the population in year 2011, right? Okay. And they're going to add to that the net change in the population, okay? How do we take the net change if we're given a rate here? What do we have to do with that rate? Integrate it. Okay. And we're going to integrate from what to what? This 123 is in the year 2011, so that's time t equals 1. And we want to integrate up to 4 because we want to get to 2014. Okay. All right. And again, this then will be the population change, okay, from 2011 to 2014. Okay, now mine really small there, but I want to save space. Okay, which is then equal to 123 plus the integral 1 to 4 of our function there, t squared plus 3t minus 30 over t squared minus 25. Okay. So there's something that we can do here, a strategy from the past. Yes, Lander. Yes, long division, right? What kind of clued you in here that we could use some long division here? Yes. Okay, exponents, right? Our powers are the same here, so we can do some simplification. Right? We can do some simplification here. So let's do that to help ourselves out. All right, so long division, right? Wow, we're going to put some long division in with partial fractions. How did you guys get so lucky? I don't know. Okay, I'm going to put in my placeholder there. Okay, t squared plus 0t minus 25 divided into t squared plus 3t minus 30. So let's see, I need 1. 1 times t squared is t squared. 1 times 0t is 0t. 1 times minus 25 is minus 25. And we'll subtract that quantity or add the opposites. So t squareds cancel. 3t and 0t is 3t. Negative 30 and 25 is negative 5. Okay, so this is really equal to 123 plus the integral from 1 to 4 of 1 dt plus the integral from 1 to 4 of a remainder there, 3t minus 5 over t squared minus 25. And now to integrate 3t minus 5 over t squared minus 25, we're going to use partial fractions. Okay. So I'm going to do that work for the partial fraction over here on the side. Okay, I guess I can do some of the work here. So we'll go ahead and do 123. Integral of 1 is just going to be t, and we're going to evaluate that from 1 to 4, and then I'm going to hold off on what this is going to be over here until we do the partial fractions. So we'll have 3t minus 5 over t plus 5, t minus 5 equals a over t plus 5 plus b over t minus 5. Okay, so you get 3t minus 5 equals a times t minus 5 plus b times t plus 5. So what's a good strategic choice of t here? 5. Okay, so if t is 5, we're going to end up with, let's see, 15. So 10 equals 10b. So b is 1. And we'll use t equals negative 5 for our other strategic choice there. And we'll end up with negative 20 equals negative 10a. So a is 2. So if that's the case, then we can break up this to be 1 to 4, excuse me, of 2 over t plus 5 dt, plus the integral from 1 to 4 of 1 over t minus 5 dt. So good. And so we end up with then t evaluated from 1 to 4 is going to be 3, right? 4, take away 1, so it's going to be 3 there. Plus, and then we'll have twice the natural log of the absolute value of t plus 5 plus natural log of the absolute value of t minus 5, and that will be evaluated from 1 to 4. So I'll go ahead and put the 123 together with 3, make it 126. Okay, and let's see here. So we'll have 2 ln of 9 plus ln of 1 is going to be 0. Minus, and then let's see here, 2 ln of 6. And then 1 minus 5 would be negative 4 plus ln of 4 there. Okay, and then if we were really feeling this, let's see, it'll be minus, so let's see, 36 times 4, 78. This way, 144, right? Okay. So we could say, let's see here. We could say natural log of 81 over, and then that would be 36 times 4 there. So natural log of 81 over 144, which would simplify 9/16. Oops, plus. Okay, but again, is that necessary? Not necessarily, right? We could just stop right there because it's, again, if it's free response or something like that. But could we simplify it down that far? Yes, it does simplify down that far. Okay. And again, just use the properties of logarithms there. Okay, so question, Cassie? Yes. All right, last one, we're going to make it. You're not that excited, I know. All right, so here is, because again, these problems take a lot of time, right? As complained by many of you, or thoughtfully complained about by many of you. Okay, right? They take a lot of time. But here's an example of an actual AP style question that we should be able to do. So why don't you go ahead and give this one a try? Okay, example number 6 there. Think about what's it got to be, A, B, C, or D here. Okay, we know that we're able to decompose it. We can see that we can maybe decompose it here to be A over x minus 1 plus B over x minus 5. So I'll let you guys go from there. See if you can figure it out. Homework will be on Google Classroom.
The problem is, you're right, they calculated it out, but where is that? You need to have parentheses around the whole thing, negative one. Right.
So.
No, I'm good at this. So if x is 5 is what it's still on my desk. Oh, careful. It's x minus. So that's gonna correct. Okay, these are good.
That's what Mario got. Mario beat you up.
Okay, sorry. Run out of time. Just go ahead and post it.
Okay. Final answer is A. All right. A. So homework will be posted here to the Google Classroom in just a moment. Is it a lot? Good question. Let me check here. I mean, I guess I should maybe give you more, so it's gonna have more time, right?
It's really okay. These are good.
All right.
All I need is in real life.
Well, I think we're in real life right now.